welcome back to another video. This is honestly one of my favorite videos for Calculus 2 because this really combines calculus from the three main sections. So we've covered derivatives, obviously, firstly. Well, we covered limits first, but limits are kind of an overarching theme. We use limits all the time. The main theories were derivatives, integrals, and series. So we've covered all three to the extent that we have to. And we found a way to accurately model functions as power series, or at least some functions as power series, mostly those rational functions. But I would like to now figure out how we can do calculus with these power series. Because the end goal of this course is to have a way to take a function, if I have f of x, I can make that into a series, an infinite series of n equals 0 to infinity of some c sub n times x minus a to the n. And then from that, I can perform derivatives on that series, or I can perform integrals on that series. And what's really cool about that is we are no longer constricted to our integration techniques and our derivative rules. Because as you're going to see, taking derivatives and integrals of power series is actually quite a trivial affair. So we're going to look at that right now. Stay tuned. Here we go. So our first definition, and just so you know, a video just like this will be coming out next to discuss how this works with integrals. But here's a definition. So if we have a power series that has a radius of convergence r, so if we have a power series centered at a, we can go r to r, and then we have some sort of interval, and then this is r minus a, and here we have r plus a, or actually a plus r, a minus r. Oops. So then we can say f of x can be defined by some power series, and it is differentiable on its radius of convergence. Because as you might recognize, this generates a polynomial. We all know that polynomials are convergent. So, or polynomials are continuous, convergence. I don't know why I've got that on the mind for this unit, but yeah, it's been a while since we've been dealing with continuity. It's been about 100 videos. F of x is differentiable on the radius of convergence, on the interval of convergence. And the way that we find the derivative of this function is we use the power rule. So it's really easy. If I want to take the derivative of this thing underlined in red, then I'm just going to use the power rule. We're differentiating we can use a linearity property with the sigma notation that we discussed back in Unit 4 or something. But if I want to take the derivative of the sum of a, then I can take the sum of the derivative of a. So what we can do is we can take the derivative of this term here, and, well, obviously, this is a very easy thing to do. We just need to use the power rule. So we get the sum from n equals 1 to infinity of n times c sub n times x minus a to the n minus 1th power. It's as easy as using the power rule, and you'll see in the next video it's a very similar affair for integrals. And we also increase the guy here just because we're lowering that power, so we won't be able to start at 0. You could always add an n plus 1 term at the other end to let it start at 0, but for now we don't need to worry about that. That's a matter of convention, in my opinion. Okay, let's try out an example with this. So, example. So find a representation for f of x as a power series. All right, so we did a very similar thing in the last video, but now we're going to need to take a derivative, and you're going to see how this is a lot easier. So I want to find a power series representation for f of x equals 1 over 1 minus x quantity squared. Okay, so you might think we're kind of screwed here. Well, we've got this term in the square, and if I wanted to get orders of x in the denominator, we'd need to separate this into two power series and then do partial fractions. And then we could work from there to try to make this look like our general power series. But if you're a student of calculus, you would note that that if I start with our general formula, if I differentiate this, use the chain rule, I set this equal to u, well, then what we end up getting is a exact replica of this guy. We get 1 over 1 minus x squared if I differentiate. So I recognize that f of x is equal to the derivative of 1 over 1 minus x, which is great. So I also know the power series representation for 1 minus x. This is equal to the sum of x to the power n. So we can differentiate that, and that's one of the easiest derivatives, just applying the power rule. So we get the sum from n equals 1. We start at n equals 1 to infinity of n times x to the n minus 1th power. All right, so now we've found a general solution. So we found that 1 over 1 minus x squared is equal to the sum from n equals 0 to infinity of n times x to the n minus 1 power, and we add an n plus 1 term here because we're starting there. All right, so that is how we take the derivative of a power series. So you can really think about this. There's no function we can't take the derivative of. Integrals is a little more useful, but for derivatives, if you have the need to maybe work this out as a power series, then I suppose you could. All right, thanks for watching, and we'll see you in the next video to talk about some integrals of power series.